I want to start today with a very specific, a very uncomfortable feeling that I think a lot of people in tech have felt. It's not the fear of bugs, and it's not the fear of deadlines. It's syntax fatigue.
Oh, that is a real thing. It is the exhaustion of just trying to keep up.
Exactly. You spend 3 months learning a framework, maybe it's Express for Node.js,
Mm-hmm.
or you dive deep into Spring Boot for Java. You
Yeah.
memorize the commands, you learn all the folder structures, you feel like, okay, I finally know what I'm doing.
Mm-hmm.
And then you open a job board, and suddenly everyone wants to go,
Mm-hmm.
or Rust, or some new framework that launched, last Tuesday.
And you feel like you're right back at square one.
Right. You feel like a junior developer all over again. It's terrifying.
It is, and it happens because of a really common trap. We call it the framework first approach. You're learning the tool, but you aren't necessarily learning the discipline.
You're learning how to type the code, but not why the system works.
Exactly. And that distinction between being a coder and being a true back-end engineer is what we are unpacking today. We've got a massive stack of resources here that all point to one philosophy: first principles.
The idea being that if you master the underlying concepts, the plumbing, the architecture, the data flow, the language itself becomes kind of irrelevant.
It becomes just a detail. It's like if you know how to build a house, it doesn't really matter if the hammer has a red handle or a blue one. The physics are the same.
I love that. So our mission is to walk the path of a true back-end engineer. We're going to trace the life of a request from the moment a user clicks a button all the way down to, what, a magnetic disk spinning in a data center?
That's the plan. And if we're starting from first principles, we can't even start with code. We have to start with the language the internet speaks.
Which is HTTP.
Exactly. Hypertext Transfer Protocol. Now, most people know the acronym, but the source material emphasizes one specific concept within HTTP that is the absolute bedrock of the web, and it trips up almost every new developer.
Let me guess. Statelessness.
Statelessness. It sounds technical, but the concept is actually very human, or rather distinctly non-human.
Okay, let's unpack this. Because when I talk to you, you remember what I said 5 minutes ago? That's state.
Right. Our conversation has context. But an HTTP server has total amnesia. If you send a request saying, "Hi, I'm user 123, and then 1 second later you send another request saying, "Add this book to my cart," the server looks at that second request and says, "I have absolutely no idea who you are."
It treats every single request as if it's the very first time it has ever met you.
Precisely. No memory of past interactions. Which means every single request must carry every single scrap of information needed to process it.
It's like sending a letter to a friend who burns it immediately after reading. You have to reintroduce yourself every single time.
And that's why we have things like cookies and authentication tokens. We are constantly forcing the client to remind the server, "Hey, it's me again, I'm still logged in."
Okay, got it.
And once you accept that the server knows nothing, the structure of the request itself becomes really important. The sources break it down into two main components: intent and location.
Intent and location. Okay, break that down for us.
The intent is the method, you know these:
Right.
get, post, put, delete. But a lot of junior devs, they'll treat these as interchangeable. They'll use a GET request to delete something because, hey, it works.
But that's bad engineering.
It is terrible engineering. These words have meaning. A GET request should be safe. It shouldn't change anything. A post implies you're creating something. And if you use GET to delete data, and some web crawler or a browser plugin decides to prefetch that link to speed things up,
You just accidentally deleted your entire database.
exactly. So understanding intent protects you. And then you have location, which is the URL. This brings us to the first piece of logic your code actually touches: routing.
The traffic cop.
The traffic cop. A request hits your server, and the router looks at the URL string to decide where it goes. And the key distinction here is static versus dynamic routes.
Static seems easy. Apey about. It's just a string match.
Right, but what about ape users 456? You can't write a separate function for every single user ID in the world. So a real backend engineer uses patterns. The router sees users.id, and it understands that 456 is a variable. It plucks it out and hands it to your code.
Now, there's a very practical note in the research here about versioning. I see this a lot. V1 users. Is it really necessary to put a V1 in there on day one?
It feels like over-engineering until you launch. The moment you have a mobile app installed on someone's phone, you lose control. You cannot force them to update. So if you change your API structure, maybe you rename username to username, and you don't have versioning,
The old app crashes.
the old app breaks. So V1 is basically an insurance policy. It lets the old app keep working on the old road while you build a new highway on V2.
That makes perfect sense. Okay, so we've routed the request. Now we have to talk about the payload, the data itself. The sources say that, what, 80% of the time we're dealing with JSON.
JavaScript object notation.
So why is JSON the king? I mean, we used to have XML, which felt very official.
XML was rigorous, but it was heavy. JSON won because of interoperability. I mean, think about it. Your backend might be in Python. Your iPhone app is in Swift. Your web dashboard is TypeScript. These languages can't talk to each other directly.
They all store memory differently. So JSON is the translator.
It's the text-based bridge. This is where the concept of serialization comes in. You take your fancy Python object, serialize it into a plain text JSON string, send it over the wire, and then the iPhone deserializes it back into a Swift object.
All right, let's cross the border. The data is deserialized. We are now inside the fortress. We're in the application code. And this is where the sources get really specific about architecture. They warn against spaghetti code.
Which is what happens when you just open a file and start typing. You validate the email, calculate the price, talk to the database, and send the receipt. All in one giant 500-line function.
It works, though.
It works until you need to change one tiny thing and you accidentally break everything else. To be an engineer, you need structure. The gold standard the sources point to is MVC, or layered architecture.
So let's walk through those layers. The request lands at the handler, sometimes called a controller. What is its only job?
The handler is the receptionist. It's the entry point. Its job is purely logistical. It just checks the paperwork. Is this request valid? Is the email field actually an email address? Is age a number?
But it doesn't check if the user is allowed to log in.
No, that's logic. The handler just ensures the shape of the data is correct. Then it passes that clean data to the second layer, the service layer.
The brain.
This is where the magic happens. The service layer contains your business logic. If the user buys 3 items, apply a discount. If the password matches, generate a token. This layer should not care about HTTP status codes or headers. It just solves the problem.
And finally, it needs to save the results somewhere.
Right. But the service layer shouldn't be writing raw SQL queries. That's the job of the third layer, the repository, or the data access layer.
The librarian.
Perfect analogy. The service layer says, I need the user with ID 5. The repository says, 1 moment. It goes to the shelf. The database speaks that complex SQL language, finds the record, and hands it back as a clean object.
I can already hear the skeptics. This sounds like a lot of boilerplate for a simple app.
It is. But here's the payoff. Decoupling. Imagine you want to switch databases from MySQL to Postgres. If you have a repository layer, you only rewrite that one layer. Your business logic, the really complex stuff in the service layer, it doesn't change at all.
You can swap out the foundation without tearing down the house.
Exactly.
That's the definition of future-proofing. Now, speaking of foundations, let's talk databases. The sources are incredibly opinionated here. They basically shout, just use Postgres.
Yeah, it's a very strong recommendation. For a long time, we had this, this war between SQL and NoSQL.
Structure versus flexibility.
Exactly. SQL was rigid. You had to define every column in advance. NoSQL, like MongoDB, was loose. You could just dump any JSON document in there. And developers loved NoSQL because it felt faster to build with at first.
But then you realize data needs structure.
Right. If you're building a payment system, you can't have loose data. You need guarantees. The reason Postgres is the winner for a true backend engineer is that it ends the war. It's a strict, reliable SQL database.
But it has a killer feature.
JSONB. It has a column type that stores binary JSON. So you can have your strict users table with an ID and an email, but then have a settings column that's just a blob of flexible JSON. You get the reliability of SQL with the flexibility of NoSQL. You don't have to choose anymore.
Okay, so we've picked Postgres. But just installing it doesn't make you an engineer. We need to talk about ACID. Sounds like something from chemistry class.
It's the set of guarantees that keeps your bank account accurate. Atomicity, consistency, isolation, durability. The one that impacts your daily coding the most is atomicity.
The all-or-nothing rule.
Think about a money transfer. You deduct $100 from Alice, and you add $100 to Bob. That's 2 separate steps. What happens if the server crashes right after step 1?
Alice has lost $100. Bob hasn't received it. The money just vanished.
That is unacceptable. So atomicity means you wrap those 2 steps in a transaction. The database treats them as a single unit. Either both happen successfully or neither of them do. If the crash occurs, the database automatically rolls back Alice's deduction. It protects data integrity.
That feels like something you don't appreciate until you've lost data.
Or lost money, yeah.
The other database concept the sources hammer home is indexing. They use a textbook analogy that I really like.
It's the best way to visualize it. If I give you a 1,000-page history book and say, find the chapter on Rome, and there's no index in the back, what do you have to do?
I have to flip through every single page line by line.
In database terms, that's a sequential scan. It works fine when you have 100 rows. It will crash your server when you have 1,000,000.
So an index is just a separate list, a map that says Rome is on page 400.
Yes. It's a data structure, usually a B tree, that lets the database jump instantly to the record. But, and here's both, engineering trade-off indexes aren't free. Every time you write new data to the book, you also have to update the index.
So writes get slower.
Exactly. If you index every single column, your database will crawl to a halt whenever you try to save something. Engineering is about finding that balance. What do we read most often? Index that. Leave the rest alone.
Okay, let's pivot to performance. Because even with indexes, databases are running on disks. And the sources remind us, disks are slow. RAM is fast.
Orders of magnitude faster. Reading from a disk takes milliseconds. Reading from RAM takes nanoseconds.
So the strategy is stop asking the database for the same thing over and over. This is where caching comes in.
Right. We use a tool like Redis, which is an in-memory store. The pattern is called cache aside. When a request comes in, your code checks Redis first. Do we have this data? If yes, return it instantly. That's a cache hit.
And if it's not there?
That's a cache miss. You go to the slow database, get the data, save a copy in Redis for next time, and then return it.
It sounds perfect. Why don't we just cache everything?
Because there's a famous saying in computer science, there are only two hard things in computer science: cache invalidation and naming things.
Cache invalidation. That's a fancy way of asking, when does the data get old?
Exactly. If you update a user's profile in the database, but you forget to delete the old version sitting in the cache, the user sees their old name, they refresh the page, and it's still the old name. They think your app is broken. Keeping the cache in sync with the database is one of the hardest logic problems you will face.
I want to move to the other side of performance. Caching speeds up reads. But what about heavy writes? I'm thinking about a scenario where a user uploads like a 4K video to your platform. You need to compress it, generate thumbnails, notify followers.
If you try to do all of that while the user is just staring at a loading spinner, they are going to leave. A web request should handle things in milliseconds, not minutes.
So we need to cheat. We need task queues.
We need asynchrony. The sources describe this using a producer-consumer model. Think of it like a busy restaurant kitchen.
Okay, I'm the customer. I order a steak.
You tell the waiter, that's the API. The waiter doesn't run back and start cooking the steak himself. That would block him from taking anyone else's order.
Right. He just writes it on a ticket.
He writes a ticket and sticks it on that spinning wheel thing. That wheel is the queue software, like RabbitMQ or Redis. The waiter turns to you, says, "Order received," and walks away. You get immediate confirmation.
Meanwhile, in the back.
In the back, you have the chefs. These are the background workers or consumers. They are separate programs just running behind the scenes. They see a ticket on the wheel, they grab it, and they start the heavy work of cooking.
So for our video upload.
The API says, "Upload received," instantly. The background worker picks up the file, spends 10 minutes compressing it, and then updates the database when it's done. The user experience is snappy, but the heavy lifting still happens.
It effectively decouples the user's time from the machine's time.
Precisely. And it adds reliability. If the cooking station catches fire, if the worker crashes, the ticket is still on the wheel, another chef can pick it up. You don't lose the job.
We're entering the final stretch here. We've built the API, the database, the cache, the queues. Now we have to defend it. We need to talk security.
Security is not a feature you twinkle on at the end. It's a mindset. And the sources are very clear on rule number 1. Never trust the client.
It sounds so paranoid.
You have to be. A developer might think, oh, I put a limit on the front-end form so users can't enter more than 50 characters. But a hacker doesn't use your front-end. They use tools like curl or Postman to send raw API requests directly to your server.
And they will send 10 gigabytes of data to that field just to see what happens.
Exactly, to see if your server explodes. So input validation has to happen on the server every single time.
Okay, and then there's authorization. Knowing who someone is. Authentication is different from knowing what they can do.
RBAC, role-based access control. Just because you're logged in doesn't mean you can delete the production database project. You have to check permissions on every single route.
Finally, let's talk about growth. Scaling. Every startup wants to have Google scale problems.
Usually before they even have users. But the concepts are vital. There are 2 ways to scale. vertical and horizontal.
Vertical's buying a bigger truck.
Right. More RAM, faster CPU. It's easy, but it's expensive, and eventually, you just run out of truck. You can't buy a computer with infinite RAM.
So the goal is horizontal scaling, buying a whole fleet of vans.
Adding more servers. Instead of one server handling 1,000 requests, you have 10 servers handling 100 each. But this loops us all the way back to the beginning, to our very first topic.
Statelessness.
Yes. You can only scale horizontally if your servers are stateless. Imagine you store the user's login session in the local memory of server A. The next request gets routed to server B. Well, server B doesn't have that memory. The user gets logged out.
So for horizontal scaling to work, server A and server B have to be identical clones.
Exactly. They are cattle, not pets. You don't name them, you spin them up and destroy them at will. All the memory must be pushed out to the Redis cache or the Postgres database. That is the only way to build a system that can truly grow.
It's really a cohesive picture. When you look at it this way, the syntax fatigue we started with, it just seems smaller.
It really is. I mean, if you understand HTTP, MVC, ACID, caching, and statelessness, those are the invariants. They haven't really changed much in 20 years.
So if I learn this and my boss tells me we're switching to a new language next week,
You just say, okay, show me the router library, show me the database driver. The rest is just logic you already know. You're not learning how to build a backend. You're just learning a new dialect.
that is a liberating thought. You're building a career on bedrock, not on the shifting sands of whatever framework is trending on Twitter this week.
That's the difference between a coder and a software engineer.
I love that.
Mm.
Now, before we go, I want to leave the listener with one final provocation from the notes. We spent all this time talking about technical scalability adding servers. But the sources hint at an even harder problem, team scalability.
Oh, that is the final boss.
Right. When you have one developer, a monolith MVC app is perfect. But what happens when you have 100 developers all trying to merge code into the same repository every day?
You start stepping on each other's toes.
Yeah.
The conflict becomes unmanageable.
Exactly. And that is where the conversation shifts to microservices. Not because the code needs it, but because the organization needs it. Breaking the app apart so Team A can break things without stopping Team B.
But that brings a whole new world of pain. Distributed systems, network latency, eventual
A
consistency.
topic for other deep dive, I think.
Definitely.
Listeners, thank you for walking the path with us today. Go build something sturdy. We'll see you next time.